Okay, now we're going to review a little bit on solubility product, and we're going to basically fold into that. We looked a little bit about common ion effects with solubility product when we looked at equilibrium, but because we had not gotten to pH at that point, we really didn't look at how does pH affect it. So we're going to kind of review a little bit and then add to that how you deal with the pH and solubility. Okay, solubility product, remember, is the equilibrium expression when you're talking about a solid dissolving in water. All right, so KSP, that's our specific equilibrium constant for a dissolving process. All right, so here's an example. I've seen this one before. KSP, there's our expression. All right. Here's if it were magnesium fluoride, silver carbonate would look like that, calcium phosphate, equilibrium expression looks like that. Okay, so we treat them the same way as we've always done equilibrium expressions, except with solubility products, your reactant is always a solid, and so it does not appear in the equilibrium expression. Okay. All right. If we're looking at, we use the same kind of techniques as we did with any other equilibrium situation. If we're not at equilibrium, we compare our initial conditions. We find Q. We call that the reaction quotient. We find Q. If Q is less than the equilibrium constant, we have an unsaturated solution, okay, which means we don't have any solid forming yet. If they're equal, we have a saturated solution, okay, which again means it's everything's dissolved, but it's at the point where it can't dissolve anymore. And then if Q is greater than the K, we have a supersaturated solution, which means we're going to see a precipitate. We're going to see some of that solid crystallize out of solution. Okay, so here's an example that we did here. Now, this was a key thing to remember, the difference between the solubility product constant and the solubility. The solubility is the concentration or the molarity that dissolves, all right, which means, and given this, for every 1 of this bismuth sulfide, we get 2 moles of bismuth and 3 moles of sulfide. So if I want to know how many moles of bismuth sulfide could dissolve in solution, it would be equal to half of the molarity of the bismuth ions that were in solution at that point, or a third of the molarity of the sulfide ions that were in solution. Okay, the KSP is constant. That's the equilibrium constant. It doesn't change unless you change the temperature. But the solubility will be variable. All right, and we've looked at the reasons it varies. If we have a common ion present, then it's going to be different. Okay, here's, again, distinguishing between, if I know the solubility, I can use that to find the KSP, the equilibrium constant. If I know the equilibrium constant, then I can use that to find the solubility. But they are 2 different things. All right, so here's an example. What is the solubility of silver chloride? All right, again, so 1.6 times 10 to the minus 10th is my KSP, which is equal to, in this case, the silver times the chloride. All right, so I'm going to call them, since they're 1 to 1, it's going to be x squared. So my solubility is the square root of 1.6, 10 to the minus 10. And so 1.26 times 10 to the minus 5. So that means that at equilibrium, this will be the molarity of the silver, the molarity of the chloride, and this will be how many moles per liter of the silver chloride dissolved. That's the solubility. the KSP for silver chloride. It's from before. May need that. All right, let's see what we need. We have 0.02 molar chloride and 0.02 molar bromine. Okay, and I want to know, so let's just see here. So bromine, 0.02, chloride is 0.02, and I'm going to add some silver to that. And I want to know what concentration do I need to add so that I precipitate just the silver bromide and not the chloride. So let's take a look. So I have 7 times 10 to the minus 13. So that's the Ag plus and the Br minus. And I'm going to go ahead and put this one over here too. 1.6 times 10 to the minus 10. That is the Ag plus, and so there's the silver chloride. Okay. So the silver, I don't know what that is, but I do know that my bromide is 0.02 molar. So for this one, my silver concentration to precipitate the silver bromide, I need to have at least, how much? 7.7 minus 13 divided by 0.02, at least 3.85 times 10 to the minus 11. That concentration will start precipitating the silver bromide. But let's see for the silver chloride, at what point do I start precipitating that? So we do the same thing. And so I get 8 times 10 to the minus 9th molar. So as long as I need at least this concentration of the silver, and I'll start precipitating silver bromide, and as long as I do not exceed this concentration, then only silver bromide will come out. Once I get beyond 8 times 10 to the minus 9th molar, then the silver chloride will also start to precipitate. Okay, we talked about how common ion is going to decrease the solubility, but let's take a look at what the difference would be. So silver bromide, I said was, sorry about this, 7.7 times 10 to the minus 13th. Alright, so this is 7.7 times 10 to the minus 13th. That's my KSP. Alright, and so let's look. So in pure water, my solubility, so KSP is my silver, my bromide, and again, these are 1-to-1 with the solid. 1 mole of the solid will give me 1 mole of silver, 1 mole of bromine. So in pure water, all right, so that's how much of the silver bromide, it's how much silver will be dissolved, how much bromide will be dissolved, and how many moles per liter of the silver bromide dissolved. But if it's not pure water, say instead that my bromine, I've added another substance. So my KSP is still the same. That defines that ratio. But now, I don't know what my silver is going to be, but I know that bromine is going to be dominated by that added sodium bromide. So the moles of silver per liter is going to tell me how much of the silver bromide dissolved. It's going to be 1-to-1. So minus 13th divided by 0.0. So 7.7 times 10 to the minus 10. So as you can see here, if I have a common ion, as you would expect, it's going to shift the equilibrium to the left, which means not as much of the solid is going to dissolve. Now, pH and solubility. There are some salts that are sensitive to pH. In other words, the changing the pH will either they have a common ion, or they will react with the acid or the base. Something will happen that is going to decrease the solubility. So let's take a look here and see what's going on. All right, so for example, here's magnesium hydroxide. All right, not especially soluble. Has a KSP of 1.2 times 10 to the minus 11. So if we take a look at that, it's normal solubility. All right, so in water, regular water, 1.4 times 10 to the minus 4 moles per liter of magnesium hydroxide will dissolve. Now, what if, okay, or that gives us a hydroxide concentration of 2.8 times 10 to the minus 4, and we have a pH of 10.45, is typically what we will see when it's dissolved, when it's saturated. Okay, so what does that mean? Well, at a pH less than that, which means you have a lower hydroxide, it's going to increase the solubility. Okay, why? Because if I am, again, Le Chatelier, if I'm removing hydroxides, or if this hydroxide is lower than that, what's it going to do? It's going to shift it right, which increases solubility. Okay? Then, if I'm greater than 10.45, which means, again, I'm increasing the hydroxide, what is that going to do? It's going to shift it left, which means I'm going to decrease the solubility. Okay? So this is kind of an example where we have a common ion, and this common ion just happens to be something that is affecting the pH, or susceptible to changes in the pH, and so we can increase or decrease the pH is basically increasing and decreasing this common ion, which is going to increase or decrease the solubility of the substance. So similar thing as in talking about common ion, except that with pH, changes in the pH can increase or decrease the solubility depending on the substance.